Hello, everyone, and welcome to Season 3, Episode 2 of the Wolfram Student Podcast. I'm Tiani, and I'm your host. This is the Wolfram Student Podcast, where each episode we dive into a new innovative project done by high schoolers using the Wolfram language. For this episode, let's welcome Ethan, who will be discussing his project on optimizing the thrust to power consumption ratio for ion thrusters through simulations. Hi, Ethan.
Hello. Yeah, so I'm Ethan. I'm from Hong Kong and I go to Hong Kong International School and I'm a senior this year.
All right, thank you so much. So to start off with, could you give us kind of a brief overview of what your experience is with Wolfram, what camps you've done, and different projects that you've done?
So I did WSRP 2023 and then I was selected for WELP for the same year and also did TA training and then went back to WSRP for 2024 as a student as well because I wanted to do another project.
Great.
Yeah.
Um, and just a classic question that we like to ask people when they come onto the podcast is, what is your favorite Wolfram function?
I think my favorite Wolfram function is honestly it's pretty basic. It's modular because I think it's just so useful to be able to just generate to create variables that are completely isolated from everything else.
Yes, yes, definitely. I agree. Module is quite the classic. I know that I personally use it all the time. All right, fantastic. So I'm excited to hear about what you did for your project. Could you give us just a quick overview of what you did?
Yeah, so in my project, what I did was I created my own simulations of multiple different types of ion thrusters, which and ion thrusters are used for aerospace engineering and just rocketry in general for deep space exploration because they're able to have really high fuel efficiency. So they're able to run for like hundreds of days without running out of fuel, which is able to give the satellite a lot of speed. And so, but one problem with ion thrusters is that they use a lot of energy, use a lot of electricity. And so what I did was I tried to optimize for the highest amount of thrust with the lowest amount of power consumption by designing my own simulations in the Wolfram language and then running lots of simulations to find the lowest thrust to power consumption ratio in Hall effect thrusters and gridded ion thrusters.
All right. Well, that sounds super, super interesting. Let's get into it.
Yeah, so like what I said before, that there are lots of issues with ion thrusters right now and regarding their power consumption ratio, right? But then the ion thrusters, like most rocket thrusters and most rocket engines, they have lots of different parameters. And so what I did was I optimized for like different parameters within and different between different thrusters, like the anode radius, the radius of like the anode radius of like the magnets, the thickness of each thrusters. And so we'll get right into it, right? So for the gridded ion thruster, it's a type of thruster which you can see in this diagram where it shoots out electrons and it also shoots out propellant, typically a heavy inert gas propellant like argon or xenon. And the electrons are also shot out, which ionizes the propellant, which is which is then shot forwards through these positively and negatively charged grids, and the positive ions are accelerated through the grid and are accelerated out of the ion thruster to be able to achieve speeds of up to like 120 kilometers per second actually. So and also it and since the mass of the propellant is so small, the thrust is actually extremely small as well, but they're also able to last a lot of time. This is like the main benefit of the thruster. And so what I did was in in my project, I defined lots of the basic parameters like the outer radius and thickness of the anode of which is the positively charged which is the charged parts of the thruster. And so I just plotted them out in Wolfram. I made the basic shape of, you can see like the hollow cylindrical cone. And they also made the positively and negatively charged grid regions, uh, as as seen in the green and red discs. And I just
Mhm.
plotted them all together. And so obviously we just having the shape, we can't do anything. So I needed to also give them the electrostatic field and electrostatic charges within for the thrusters. So the anode is positively charged, and then the screening grid here is it's negatively charged, but it's weaker. It's and then this accelerating grid is positively charged, but this accelerating grid is charged more positively than the screening grid. So when the electron passes through between the first and the second grid, it accelerates a huge amount. And so what I did was I found the typical charge densities for these gridded ion thrusters here, and I used Poisson's equations to solve for the electric potential within the entire domain. As you can see here, and take the Laplacian and also the electric potential, and yeah, that's just the equation. And so I just solved for I used the partial differentiation equations function to solve for the Laplacian function of uh, the thruster, and then also found the boundary conditions, and just use Wolfram's ND solve to just figure out a rough estimate of the electrostatic potential at each point. And then I plotted the graph out as you could see before for the electrostatic potential based
So,
on the three parts.
a
Sorry?
quick question. Yeah, so for your charge densities that you used further up, are
Yes.
those just ones that um you found that sorry, I think further
Here.
down. Yeah. Are these just values that you found like off
Yeah, these are
Google
values I
Maps?
found like on NASA's websites on ion thrusters that they've already used before
Okay, so for like a similar type thruster, these are like the like empirical values that they found, so then you were
that
able
have
to
been
plug them
used.
in.
Yeah, yeah,
Okay,
from
I
like
see.
NASA's next sea thrusters.
Okay, all
Yeah,
right.
and then uh, given the electrostatic field, I also inputted basic basic values of like the initial velocity of like I assumed the initial velocity of of the propellant gun, and also and also like the the charge of the ion. I just use xenon. That's a very typical propellant. I use xenon. I use the charge with xenon. I found the mass of the xenon of a single xenon ion. And then I so what I did was I found the electric field forces using the electrostatic field from here from above that we calculated. And I just plug them into the equations of motion, the typical equations of motion to find like the forces enacting upon the ion at each individual point. And so what I did was I just used Wolfram again to solve through for the equation of motion as just following the ion through small steps into until it leaves the domain from the beginning, like from inside the
Mm.
thruster, and just solving each equation individually and finding the acceleration and velocity at each point. And so here we then plot the trajectory of the ion. You can see it just shoots straight out. And we can also see like the velocity over time. It's reaching up to like 120 meters per second. Oh yeah, they reach 120 meters per 120,000 meters per second, 120 kilometers per second. And you can also see like the acceleration over time. There's a huge spike and then slowly drops down. And here I think this is what is able to like more more accurately confirm that the simulation is somewhat accurate, because as you can see here, there's a large spike in acceleration between point 0.1 and 0.2 meters in the z-axis. And if you look through here, it's hard to see. Yeah, if you look through here, 0.1 to 0.2 is right between where the two screening and accelerating grids are, and that's where the main part of the highest amount of acceleration occurs. Um, and so that's a good like indication of, oh, okay, my simulation is correct. And so from the graphs, we extract the maximum velocity and maximum acceleration. And I use that to calculate the mass flow rate, which is just the neutral density of the ion multiplied by the cross sectional area of the thruster multiplied the ion mass multiplied by the ionization rate, which I assume to be 0.7, which is also like a typical value of like what percentage of the xenon gas is actually ionized. And through that, I'm able to calculate the actual amount of thrust and specific impulse that is generated from just by from my simulation, and we're able to see, oh, it's able to from this set of parameters that I defined up here of like 0.4 meters of the outer radius, like 0.04 meters of the thickness of the anode. This is the anode, by the way. Yeah. From like these different parameters that I defined, like the spacing and the grid height and the radius and the thickness, we're able to find out, oh, it's able to generate 0.816 newtons of thrust, and it has a specific impulse of 9,370. And um and through that we're able to also calculate the power consumption, which is just the ionization energy, like the energy it requires to ionize that one a singular ion multiplied by the number of ions per second that are being shot out, which is the mass flow rate divided by the ion mass, and we get the ionization power by multiplying the two together. And through that, we're able to see it's consuming 76,000 watts. 76,000 watts. It takes 76,000 watts to operate this ion thruster, and we're then able to calculate the thrust to power consumption ratio.
Okay, just a quick
Uh,
question. So further up,
yes,
where you have the one where you're kind of modeling the trajectory, yeah, for the ion.
yes,
So for that, the purple line is like where it would go, like where the trajectory
yes,
is.
yeah,
Um,
where the ion's going.
are all of the ions like in the middle of your thruster, or are you kind of just assuming that like kind of across the entirety of the surface, they all will follow like a similar trajectory?
Yeah, that's what I'm assuming. I'm just assuming like, oh, I'll just place it in the middle and then I'll multiply by the area of the thruster volume, and it will be about the same. It'll be about similar. Because if I were to run like the millions of ions, it'd be way too
Yeah.
computationally intensive.
Right, right. And then the
Yeah.
other quick question I had is like for when you're setting the parameters, so for example, like the thickness of it as like zero point 0.4 or like 0.04, how are you getting these
Oh, I'll
radiuses
actually
and
go
things?
through this later. So what I did is that I from all my functions above, I just put them all into one singular function that's able to calculate the thrust to power consumption ratio. And I'm just discarding all the plots because we don't need that.
Mm.
And so here are like the plausible ranges for each parameter. And I got all of these from also I just searched up like different types of ion thrusters, and I just found the largest one and found the like the smallest grid ion thruster I could find, the largest one I could find, and I just put those in the plausible ranges. I actually turned my Wolfram community post into a proper research papers, and that one has a lot more of the citations that aren't linked here. But I have citations at the bottom, but they're just not linked individually. Yeah, so you can see like anode radius is like 0.05 to 0.4 meters is these are all like plausible ranges. And so here, like I said, I created a function that would just calculate the thrust to power consumption ratio, give me like the parameters I inputted, and then like the exhaust velocity, thrust, specific impulse power, and thrust to power ratio. That would be calculated from this specific like these specific parameters. And what I did was I just ran the results for using using the Wolfram function of like a parallel map, which computes all of the functions simultaneously, like using like the 6 cores I have on my computer, the 6 CPU cores, so it makes everything much faster. And I ran them through like a combination of every single parameter, which had around like 6,400 different combinations. And through this, through all the results, I labeled them and just turned them into a matrix. Uh, and I turned it into a correlation matrix using the Wolfram correlation function. And here you can see like which um which which parameters affect which different results the most. As you can see here, like the anode radius is really important at increasing like the thrust, but it also hugely increases the power. And here, like anode thickness is also increases the thrust. There's a high correlation of 0.47 to with thrust, but also it's also able to decrease it also highly decreases the thrust to power consumption ratio, which isn't good. So we're able to see, oh, anode thickness, even though it increases thrust, we don't actually want to increase that by too much. And so using seeing all of that, I also filtered through all the data I had and just sorted through for parameters that maximize the thrust, and also sorted for parameters that maximize the thrust to power consumption ratio. Oh, this is a typo. Oops. Yeah, power. And we're able to see that we're able to generate 0.00. This doesn't really mean much, but we're able to generate around 26 millinewtons of thrust while consuming only 360 watts of power here. We're able to generate 0.026 newtons and 26 millinewtons, all consuming 360 watts. Whereas like the typical ion thruster is only needs like 1,000 watts to generate the same amount of thrust. And so here we're able to see, oh, we're almost like a third. We're able to slash the energy. We're able to increase energy efficiency by like 3 times. And then I also did like a very similar process with the Hall effect thruster, which is very similar, but it also includes a magnetic field that balances all the electrons to be more focused. And the electrons are shot out through the middle, and they're used to, and the magnets are able to trap all the electrons in a circular motion through the Hall effect, and there it's able to ionize the gas that's injected through the channels and is shot out later. So I did the same thing. I defined all basic radiuses, basic parameters, and like radiuses and thicknesses, and just to create a first initial simulation. And we can just skip through these. This is like the cathode region. This is like the anode region of the cathode and anode regions of the Hall effect thruster. There's like, and this is what the magnets look like. This is what the outer magnets look like. I made them blue and red for like the north and south. And here you can see like a full Hall thruster. It looks quite similar, but it actually doesn't look that similar. This one looks a lot. Yeah, this one, it looks pretty cool, I think. And here we also need to generate the electrostatic field just as above with the gridded ion thrusters. And so we defined default charge densities that I found online. And same thing, I used the Poisson equation, and I found the potential electric field for each point on the graph, and then I graphed it out. And you can see the electrostatic field. And we also, since it's a Hall effect thruster, the Hall effect also it's mainly because of the magnetic field. It also has two diamagnetic magnets. So I think that's just two oppositely faced magnets in the inside and outside that creates a circular magnetic field that traps all the electrons inside. And so these are basic values of like magnetic permeability, and also define like the magnetic field strength of the magnets to be like 0.02 Teslas, which is also like a typical value of these Hall effect thrusters. And then I used the Biot-Savart law to find the magnetic field through th through the entire domain. And this is the law here. Yeah, I just used Wolfram to just generate this. Is all just a lot of math, just using the Biot-Savart law. And then yeah, and here I'm plotting both the electrostatic field and the magnetic field together. And here you can see like the magnet from the, oh, I don't know why that happens. I think it's up here. You're able to see like from
Yeah.
the magnetic fields coming from the inner magnets and then circling around to the outer magnets. Same with both sides, and that's this magnetic field is what traps the electrons circling around in the middle. And having seen that, we can then calculate the trajectory of the ion again, and you just define initial position, initial velocities. Same thing is up there. And then with the equations of motion, I also added the magnetic field strengths, magnetic field forces into the equations of motion that also affect how the ion moves at the trajectory of the ion, which is calculated here. And same thing, I just plotted out the trajectory of the ion. And you just see it going up in the green line. And I also graphed out the acceleration velocity of the ion again. You didn't see the acceleration versus time. and also see the velocity versus the z coordinate of the Hall thruster of the space. And you can see it's a Hall thruster actually has a lower typically has a lower exhaust velocity of only around 20,000 meters per second. And did the same thing. I calculate the thrust using the mass flow rate. Here, it's able to generate 0.19 newtons of thrust compared to like the 0.28 from above. And like it has a much lower specific impulse. And it's using like 2,200 watts of power, which is less than the gridded ion thruster. And we're able to see the thrust to power ratio as well, right here. And so, this is the interesting part of my project, where I also compared my simulations to empirical data from like the Wolfram, not the Wolfram, from the University of Michigan's Plasma Dynamics and Electric Propulsion Lab. And they had a proper Hall effect thruster. They had a physical Hall effect thruster, and they measured a lot of the data that I am not able to gather from a simulation. And so what I did, I just got all they have a Julia package and I imported that Julia package and all of their data and plotted them out. And here you can see like the neutral density, a lot of the different graphs of like the ion velocity. And here there's around like and the difference between my thruster and my simulations and theirs is that mine automatically assumes the ion is already ionized and it has an initial starting velocity and the ion continues to move ion continues to have a trajectory outside of the thruster. But the difference with this with the empirical data is that the data only measures from the wall of the Hall effect thruster from the very most left side all the way to just when the second it exits the Hall effect thruster. And so it's unable to measure the acceleration that's carried forwards from that is still carried forward from the Hall effect thruster, and it tapers up early, and it also has a different acceleration velocity curve because it's the atoms are not immediately ionized, whereas mine are immediately ionized. That's why the velocity plots are different. And comparing the simulations, we're able to see that what I did, I just took the data from these different simulations and I just calculated the thrust and velocity, calculated the thrust for both simulations, and I also compared like the velocity plots. They have a quite similar exit a final velocity, but like I said, the difference in the trajectory is quite large, as mine makes a lot of assumptions. And we also see like, oh, the exhaust velocity is right. It's within like 1,000 meters per second, and the thrust is also within 2 millinewtons, which to me is it shows that it doesn't prove congruence, but it shows that my simulations have a slight basis in reality, and it's not complete bogus numbers. And with the same thing, and knowing that my simulations are somewhat accurate, I ran all the simulations like the same. I put all the functions in my favorite module function, my favorite module Wolfram function. I put all the functions above into this function that's able to, just like above, give me all the parameters I input in, all the values I want to see, and then I'm able to see all the parameters and the ranges of like possible values, and I just run all of them and get the results. And then using the results, I once again created another correlation matrix, and much more similarly, there's a much higher negative correlation between the anode thickness and the thrust to power consumption ratio. There's also a negative correlation between like velocity and thrust to power ratio, which is which shows that the lower the velocity, the better the thrust to power consumption ratio will be, which is quite interesting because it shows that if you're trying to increase thrust, you can't really you're trying to increase the velocity, you're trying to increase thrust, you can't really increase the power to consumption ratio much. But also you're also able to see that the Hall effect thruster is much more energy efficient because many of these thrust to power consumption ratio values are negative, which shows that even though you're increasing the radius, it's a much more the Hall effect thruster is it's actually less efficient because all these values are negative and it's harder to increase the thrust to power consumption ratio. And using the same method, I found like the highest amount of thrust we're able to generate, and I also found the highest we also found like the ability to maximize the thrust to power consumption ratio, creating 185 millinewtons of thrust. And here we're able to create 19 newtons of thrust, which is actually quite high. But this is taking up over like a million watts, which is insane. And here's like compared to like comparing my simulation results to empirical data from NASA, we're able to see that my theoretical maximum is 185 millinewtons, consuming like 2000 watts, while the typical Hall thruster consumes 1350 watts and produces 83 millinewtons. So based on our results, I'm able to increase the thrust by like around 2.22 times while only increasing the power consumption by 1.456, which to me I believe is a success.
Yep. I
And
have two quick questions.
yes,
So the first of which is like, uh, so like from what I know, like launching rockets, or like satellites and things is really expensive.
yes,
So it makes sense that like, so to me it seems like a lot of your ratios are like, quite significant. Like for example, 1.5 times or something. Um, did you ever look at what your like optimized parameters were at the end and then
yeah.
compare them into like some of the ones that you looked at initially to see if there are any that had like similar parameters to the ones that you thought were optimal?
Oh, that's actually a really good idea. I should have done that. I did not. Yeah, but you can see like the optimal parameters. You have like 0.2 for the anode radius and 0.005 for the thickness. Maybe I should have. Yeah, I think that would have been a really good idea to find the parameters for the thrusters I'm comparing to. Yeah, I
Yeah,
think that
yeah,
yeah,
'cause
I
I
did
think
not
like
do that.
1.5 times or like 3 times is like a lot, so it would have been interesting to see. And
Yeah.
then my other question is just like running all of these simulations, it seems like a lot of code. Like, how long did they take to run? And did you have any issues with like having all your code like run in time?
Yeah. It's a funny question. These took over like so in 2023 like I did like a very similar project of of doing simulations and running them, and that then there took like 16 hours to run. So this year I got a
Oh,
new laptop and it was much faster and it only took 8 hours. So I'm thinking like
okay.
if I didn't get a new laptop, it would have taken like 20 plus hours to run it. But yeah, I guess like it's engineering. It's like this is why like CFD software is so expensive because like they're able to optimize it so well, make it run quickly. It's like it's really like an eye-opening experience of like how difficult it is to do proper engineering. And this is still with a lot of different assumptions that I'm not calculating.
All right.
Yeah.
Um, yeah, I'm interested to hear like what is something maybe you want to do next with this project, or with Wolfram as a whole.
With this project, I would definitely like to uh work and work more with the Julia package and try and compare not compare and try and use their data to improve my simulations. And I would also like to like you said, compare my results to these existing thrusters and figure out what makes it so much better. I'd also like to definitely take a lot into account like the ionization process and like the plasma friction, because those are very important assumptions that I assume negligible, although in the real world they're very much non-negligible, and those also take a lot more energy and highly reduces the efficiency.
Yeah, I think it's really cool that you were able to bring in like the real world data. So, with like the Julia package, so there's definitely a lot that you could do in that domain. And I'm really
Yeah,
excited to see it. All
yeah.
right.
Thank you,
Well, good luck on all your future projects. And thank you so much for coming on the podcast and sharing.
thank you,
Thanks for listening to this episode of the Wolfram Student Podcast. We hope you learned something new and took away insights from today's discussion. If you want to learn more about Wolfram, summer programs, research opportunities, or be featured in a future episode, check out the links in the description below. Be sure to tune back in to check out our next episode. This is your host, Tiani Gu, and thanks for listening to this episode of the Wolfram Student Podcast.